In this video, I'm going to cover section 2.1, unions of events and addition rules. So the let's see, first one, let me start with the example 2.15. So tables list the history of 940 the wafers in a semiconductor manufacturing process. So suppose that one wafer is selected at random. So let H denote the event that the wafer contains high levels of contaminations. Then P of H is going to be 358 over 940. So then it makes sense because probability H applying the see that the suppose that one wafer is selected random, then what we're gonna apply the classical probability. So P of H gonna be number of outcomes in the event divided by number of outcomes in sample space. So here in the sample space has 940 wafers, right? And what's the event? So H, in this case, H is what denote the event that the wafer contain high level of contaminations. How many outcomes? I mean, how many wafers contaminated with a high level? So 358, right? So that's why P of H is that fraction. Okay, so now let's see denote the event that the wafer is in the center of the sputtering tool. Then P of C is 6 to 6 divided by 940. Yep, makes sense. Why? What's C? C denote the what wafer in the center of the sputtering tool. So right here, 6 to 6. Okay, this many wafer is in the center of the sputtering tool, right? So also P probability of H intersection of C. So what is H? H is the wafers what with high level of contaminations, and then C is wafer is in the center of sputtering the tool, so which is 112 right here. Okay, so now or I mean the you can just figure out the H intersection C by drawing the Venn diagrams. Okay, so what I mean is right here. So let's say this is the let's see mm, yeah. So let's see. Yeah, never mind. Maybe during the using the Venn diagram. mm Maybe that makes more complicated. So never mind. Sorry about that. So now then, because we have too many the event, right? Center edge, I mean contaminate the low high in the contamination center edge we have four. We have to draw the four circle overlapping each others. So that is more it's kind of more complicated than just a table. So just use table. So P of H intersection C gonna be 112 over 940. Yeah, makes sense. Now then the event H union C, H union C, okay, then well you may just say, okay, so how many wafers in high contamination? 358, and then C how many wafers in the center? The 626, then just adding them up? No. I told you in the last time when I covered 2 point I think 2. So 385 only contained what? This many of wafer, right? And then that number also contained that this many of wafers, 112. So adding two numbers of 358 and then plus 626, it means that what we added 112 twice. So when you do think about the probability of H union C, then well we have to calculate that probability like this: probability H plus probability of C minus probability H intersection C. Keep in mind this: we got P of H, we got P of C, and then we got P of H intersection C. So right here, right here, and then right here, and then right here, right? So plug in those fractions into the formula, then we're gonna get this: A72 over 940. So keep in mind this. Now next one, probability union. Yeah, so Kim, this is probability union. This is you know the similar to the what? The multiplication rule. Sorry, addition rule of the event, right? So anyway, so keep in mind that addition rule of the probability. Okay. So probability of the A union B is equal to P of A plus P of B minus P of A intersection B. Now then, what if A and B are mutually exclusive? Remember that mutually exclusive, it means that two events don't have what overlapping or common the outcomes. Okay, so A intersection B equals empty set. And then since A intersection B equals empty set, probability of A intersection B is gonna be 0. So P of A union B gonna be P of A plus P of B. What about the three or more events are just coupled? Yeah, it's kind of complicated, right? So P of A union B union C is equal to P of A union B union C. Now you see that? So we're gonna consider A union B as a one big event, okay? And then we apply that addition rule. Then you're gonna get this. Okay. So now then, the what about this? Give me a second. So P of A union B intersection C. So A union, you see that, or the parenthesis A union intersection C, then we can dispute the intersection C, right? So we're gonna get the A intersection C union a B intersection C. Let's see, I show you. So that is equal to, let's see, right here. Okay. By the way, let me, what is this? This is what? Oh, this is cool. So this is equal to P, applying the addition rule. This is P of A, right? Plus P of B, is it? B, and then minus P of A intersection B, right? Okay. Give me a second. All right. So yeah. So it takes it's quite takes long to write the handwriting on the screen, so I just write in the paper. So you see the P of A union B plus P of C minus P of A union B intersection C, that is equal to, see that right here, the applying the addition rule, P of A union B becomes this, P of A plus P of B minus P of A intersection B, and then we copy P of C right here. And then, see, we can apply distribute the intersection C into A and B. Then we got this: A intersection C and B intersection C, and union B intersection C. Now we're gonna consider this is one big event. Okay, maybe let's say, I don't know, maybe you know E1. Okay, and then let's say this is but one big event E2. Okay, then probability of E1 union E2, we can apply the what addition rule. Okay. Then P of E1 plus P of E2 minus P of E1 intersection E2. What's the intersection of E1 and E2? A intersection C, intersection B, intersection C. That's going to be A intersection B, intersection C. And then now we're going to distribute a negative sign for each terms. We're going to get this. Okay. And then we just copy this part right here. Okay. So now you understood it, right? So now, all right, back to the textbook. So that's why we got this. P A union B union C is equal to this. Okay. So now, the what about the all events? I'm thinking about the more more events. Okay, maybe greater than more than 3 events. And then what if all the events are mutually exclusive? Then yeah, then the probability of union of all the events going to be much easier than that 2.7. Okay, so this is just P of E1 plus P2 through the P of EK. The Venn diagram must be like that: E1, E2, E3, E4, E5, E6. Okay, there will be no intersection if all events E1 through EK are mutually exclusive each other. Okay, so now example 2.16. So here is a simple example of mutually exclusive events, which are used quite frequently. Let X denote the pH of sample. Then consider the event that X is greater than 6.5, but less than or equal to 7.8. So now, then this probability is sum of any collection of mutually exclusive event with a union equal to the same range of for X. One example is this. So we'll find a probability that, okay, the X, what's X? Sample, okay? pH sample, okay? pH sample between us, greater than 6.5 or less than or equal to 7.8. That is equal to, we can say 6 point, we're just gonna break up that probability as like this. X is equal to 6.5, greater than or equal to 6.5, less than or equal to 7.0, and the greater than 7.0, less than or equal to 7.5. And then, yeah, just kind of, the divide that interval 6.5 open 6.5, the close 7.8 to 3 intervals. And then that 3 interval don't have overlapping part at all. Okay, then applying the, that one, mutually exclusive, I mean, addition rule for the mutually exclusive event, which is this, equation 2.8, then we get this. Okay, so give me a second. We're gonna get this. I'm sorry, we're gonna get this. Okay, this is another example. Okay, I think this is it's easy to understand this, right? So that's for the 2.4. Okay, next time I'm gonna cover 2.5.